All right, our last topic in the geometry of linear transformations. Now that we know how determinants kind of tell us how linear transformations affect areas and volumes, we want to figure out how they affect lengths of vectors as well. So these last couple of topics give us an opportunity to discover the geometric properties of a linear transformation as they sort of act in one direction at a time on their domain and not just on the aggregate for the full area and the volume. And so the topics that this covers are what are called the eigenvectors and the eigenvalues of a linear transformation. The German prefix eigen, E-I-G-E-N, sort of stands for characteristic, right? It sort of means these are the ways in which a linear transformation changes the lengths of vectors that, taken together, sort of characteristically define the entire geometry of how this linear transformation acts on its domain. And so what this is going to allow us to do is something like the following. So say I have a linear transformation from 2 space into 2 space that's defined by this standard matrix, 2, 2, 0, 3 in the rows. Because I can think of both the domain and the codomain of my linear transformation as both being the xy plane, I'm going to put on here a purple vector, which is a vector which I'm inputting into my transformation, and the green vector is what's getting outputted. Right? So if I put the vector 0, 1 into this linear transformation, it's going to output the vector 2, 0, the first column. If I put in the vector, sorry, that was 1, 0. If I put in 0, 1, it's going to output the second column, the vector 2, 3. And of course, everything in between. So if we're going to ask and answer the question, how does this linear transformation affect the lengths of vectors? The first thing that I want to find are what are the vectors whose lengths are being changed by this linear transformation, but whose directions, for whatever that means, are not being changed. That's going to be the first thing that we look for. And I can do that in this little tool here just by kind of dragging my purple input vector around and finding places where the purple input vector and the green output vector are in the same direction as one another, which doesn't look like it happens here. But if I go over here far enough, I can kind of make them line up. So this purple vector right here, whatever its coordinates are, right, its image under this linear transformation lies in the same direction as the original vector did. Its length has been perhaps changed a little bit, but the direction has not. So this vector that we're seeing right here is going to be an important vector for us to take a look at, because when this linear transformation acts on that vector, it changes the length of the vector, but it doesn't change the direction. Those are the vectors we're going to be searching for. So here's one such example. But these examples don't just come in singles. As with many things in linear algebra, if we can find more than one example of them, then there will be infinitely many examples of them. And sure enough, because of linearity, if this vector is being stretched by a constant scalar factor by this linear transformation, then so is any scalar multiple of that vector, right? So this vector is also in the same direction as its image. This vector is in the same direction as its image. If I go to the other quadrant, if I multiply by a negative constant, now this vector is in the same direction as its image as well. And so these vectors, which are getting just stretched in their direction, their length is changing, but their direction is not. These vectors don't exist in isolation. They exist in entire subspaces. Those subspaces are going to be called eigenspaces for our matrix. So one eigenspace for this matrix is going to be this line that we're seeing here. All of the purple vectors that are just being stretched, their length is changing, but their direction is not. All of those vectors lie along this line, and that line is going to be what we call one of the eigenspaces of this matrix. Well, how many eigenspaces does this matrix have? We've found one of them, right? This line. Can we find some others? If I keep dragging around, well, these vectors are in a different direction from their images. But by the time I swing back around to here, oh, look, that vector is also being stretched by changing its length but not changing its direction. And so any scalar multiple of it, likewise, will have its length changed but not its direction changed. And so we found another eigenspace for this matrix. All the vectors that lie along, in this example, the x-axis. The x-axis appears to be an eigenspace because the lengths of vectors are changing, but the directions of vectors are not changing. We also call these subspaces invariant subspaces for a linear transformation, because if I take a vector, any purple vector from this space, its image is also going to be another vector in that same space. If I feed this linear transformation a vector from the x-axis, it's going to spit out for me a vector on the x-axis as well. So the x-axis is an invariant subspace for this linear transformation. Likewise, for whatever this line is. I can't see the coordinates on here well enough to get an exact equation, but whatever this line is also an invariant subspace. If I input a vector from this line into my linear transformation, it's going to output another vector from that same line out of this linear transformation. So what we're seeing here are two eigenspaces for this 2 by 2 matrix. One of them that looks like this sort of diagonalish line over here, and another that looks like it's just the x-axis. Now, the second question that I can ask is, what is actually happening to the length of vectors in these eigenspaces? To do that, I just want to divide. What's the length of the output vector divided by the length of the input vector? So, for example, on the x-axis, if I input the vector 5, 0 into this transformation, it's going to spit out, apparently, the vector 10, 0. So what has actually happened to the lengths of vectors? They've been multiplied by 2. So it looks like this linear transformation is doing nothing more than doubling the lengths of vectors on the x-axis. So that number 2 is what we call the length factor that this linear transformation is stretching the lengths of vectors by from the x-axis, which is my eigenspace. And so we call that number 2 the eigenvalue associated with the eigenspace, which in this example is the x-axis. So every vector on the x-axis is being just stretched in place by a factor of 2, and the direction is not being changed by this linear transformation. That means that the x-axis is an eigenspace for this linear transformation with an eigenvalue of 2. What about my other eigenspace? That was this one that was sort of in a diagonal direction over here. On this eigenspace, if I compare the lengths of output vectors to the lengths of the input vectors, it looks like the length of the green vector divided by the length of the purple vector here is approximately 3. Not getting the numbers to exactly line up here, but that's just the way that this app is kind of working on me here. Oop, I got it right there. I can't quite move the mouse carefully enough. There we go. So for this purple input vector, its image is the green output vector, which is just a scalar multiple. It's 3 times the original. And so this diagonalish looking line is another eigenspace for this matrix, and the eigenvalue associated with that eigenspace is 3. So every vector on this diagonalish line is getting just stretched by a factor of 3, but it's remaining in that same line. Every vector on the x-axis its image will remain on the x-axis as well, but will be twice as long. So the x-axis is an eigenspace with an eigenvalue of 2, and this diagonalish line is an eigenspace with an eigenvalue of 3. And now that I understand those two things, that sort of completely describes the entire geometry of this linear transformation for me. Because those two eigenspaces can form, vectors from those eigenspaces can form a basis of the entire domain, R2. And so any vector from 2 space can be expressed as a linear combination of vectors from those eigenspaces in one and only one way. And because I know what's happening to the lengths of those vectors individually on the eigenspaces, I can figure out what's happening to the lengths of all vectors in my vector space. So knowing the eigenspaces and the eigenvalues associated with those eigenspaces gives me a sort of a decomposed version of the determinant. When we met this matrix earlier today, we figured out that the determinant of this matrix was 6. It's changing areas by a factor of 6. And now we can see why it's changing areas by a factor of 6. Because we found one direction along which it's changing lengths by a factor of 3, and another direction along which it's changing lengths by a factor of 2. And so if it's doubling lengths in one of my eigenspace directions, and it's tripling lengths in my other eigenspace direction, then it stands to reason that it's stretching out the areas of everything by a factor of 2 times 3, which is 6. So we started today by seeing determinants, which was that overall measure of how areas and volumes changed. But now eigenvalues are giving us a way to take that apart into how the lengths are changing in each of a bunch of linearly independent, we hope, directions. In this example, the determinant of 6, the area was changing by a factor of 6 because there were 2 independent directions, one of which was changing lengths by a factor of 3, and the other of which was changing lengths by a factor of 2. And so this gives us a heuristic reason to believe, for example, that if I know what all of the eigenvalues of a linear transformation are, that they should multiply together to give me the determinant of that linear transformation, which is a true statement. Right? So how do we find the eigenspaces and eigenvalues for a linear transformation? That's going to be what we look at next to wrap up for today.